So another example that I can give you here is, what if I want to know how many tiles there were on that floor? Uh, One way you could do it is pretty much just count, but that hallway looks pretty long, so try and get the official count of tiles on all of that hallway would take a lot of time and energy. What you could do is maybe count tiles across the bottom and then tiles all the way along the length. Once you know how big your area is, you can just multiply your length times width and add up all the tiles that you would find in there. So the example there for tiles is what we call integration. Integration sounds intimidating, but it can be boiled down to really just the antiderivative, just doing the reverse of whatever you did to get a derivative. Or another name for it is the area under a curve. So if you have graphs like you're seeing down there below, if you get positive areas, that is a positive integral. If you have negative areas, that's a negative integral. Or if you have a curved graph, it's not going to give you a nice rectangular area. What you're going to need to do is make multiple rectangular areas and add up each of those little DTs all the way along that graph. So you can see they made 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 rectangles there. And what they want to do to find the area under that curve is add up all those little rectangles. Calculus has a trick to help you do those integrals without having to add up each of those little blocks. And that's the rules of integration here. There's about 5 integrals that AP is asking for. Again, you're going to use a power rule. You're going to do natural log functions, exponential functions, and sine and cosine functions. So these are the 5 basic ones they want you to do here. Like I said before, we're going to do a lot more in the future with more integrals than you have the equation sheet. But like I said, it's the antiderivative, so you can see for the very first one, we are going to add 1 to the power, and then you actually divide by the new power. For e to the x, since the derivative of e to the x was e to the x, integral of e to the x is e to the x. 1 over x goes back into natural log, and cosine becomes sine, and sine becomes negative cosine. So make sure you know those 5, but we'll do a couple practice examples here as well. For the integration examples, make sure you're following along with the guided notes. I'm going to do a power rule and a trig function to practice with you, and then I'll have specific examples that you can look up later. Okay, so the first example is an integral of x squared dx, and sometimes on our integration we put limits, or as Ms. Bergerman likes to say, bounds. The bounds for this one, I'm going to go from 0 to 4 on our bounds. I want to take the integral of x squared, and the dx just tells me which variable I'm doing the integration for. To do that, like the rule said, I'm going to add 1 to the power, so 2 becomes 3, and I'm going to divide by the new power, which is 3. And that's it. That's how you take the integral by doing the power rule. Because watch, I can take x cubed over 3 and take the derivative. That would bring the power down. 3x, drop the power by 1, squared over 3, or boom, I'm back to the very beginning of x squared. Now, when we have bounds or limits of our integration, we need to evaluate the function now with the bounds we have. My x cubed over 3 needs to be evaluated between 4 and 0. So what that means is I need to put 4 in for x, and then I need to put 0 in for x. So what I'll do is I'll do 4 cubed over 3, and you subtract the difference between your two bounds, 0 cubed over 3. And you can see, well, this side's going to be real easy. 0 cubed over 3 is going to be nothing. 4 cubed over 3 ends up being about 21.3. And that's how you evaluate a function using your bounds or limits. I go back and forth between those two words. I learned them as limits, but you guys have learned them with Ms. Brueggemann as bounds. So whatever works for you, I will try my best to say bounds every single time. The second example that I want to do with you is doing an integral of a trig function. So the integral of negative sine x dx. So you can go back to that trig table and try to figure out what that was, or we can kind of look at graphs to try and figure out what this one actually should be. Negative sine x dx ends up turning into cosine of x. And if we want to prove that, let's draw a cosine graph. Cosine graph starts like this. Starts off a positive 1, goes to 0, negative 1, back up. And the derivative of that should be 0, negative, 0, positive, 0. So let's plot those points. 0, negative, 0, positive, 0. And you can see that, yes, cosine becomes negative sine, so the reverse of negative sine must be cosine. So you can use graphs to kind of check yourself and prove that those integrals are correct. So again, if you have any questions on running through these examples, please email me, message me, let me know what you need. You have about 2 weeks left till school, so good luck to you, and see you on day 1. So in the description, there is a link for a calculus quiz based on watching this video. Make sure you take it. If you don't get 100%, click the link again, take it again, make sure you get yourself to 100%. If you have any questions, again, message me.